Good evening. Welcome back to AP Stats Notes Online. We have been talking about significance tests or hypothesis tests, as they're also called, in sort of the basics, the foundations, sort of the things that we want to look at, the calculations that we want to look for. We haven't really talked about how to calculate some of these things, and we will. We're just trying to get an idea behind a significance test. So we got to a point in the previous notes where we are talking about how to, based on a p-value and an alpha, reject our null hypothesis or fail to reject, and we'll keep talking about rejecting versus failing to reject. But in the last question we had in the previous notes is what should be considered when choosing a significance level. And you have to remember that comparing our p-value, or the probability of our sample giving us this result, whatever it is, assuming the null is true, that p-value is going to be compared to your alpha, or your significance level. And based on that comparison, you'll either reject or fail to reject your null hypothesis. So in the last question from the previous notes, what should be considered when choosing a significance level? Remember that this is alpha. We talked about the significance level should be decided before the data is produced. You don't want to produce your data, find the p-value, and then find an alpha that would help you reject the null. I mean, that's not how a valid test is performed. You're going to choose your alpha at the beginning, and your sample will either produce a statistically significant result or it won't. The appropriate significance level depends on the consequences of rejecting or failing to reject the null hypothesis. And I spoke during our activity about, and even last night in the notes, about the fact that we sort of look at a hypothesis test or a significance test as a jury trial, right? And we talked about the consequences of making mistakes, or the consequences of, guilty versus not guilty in a trial, and if there was a mistake made. And depending on which mistake you find to be the most egregious, that will dictate which mistake you want to block against, and therefore choose your significance level due to that. Okay? That's what we're going to talk about tonight, are the mistakes that can be made. So in the significance test, what two errors can we make? And we discussed this before. A type 1 error is where we reject H naught when you shouldn't have. Okay? When we reject H naught and H naught ends up being true. Okay? A type 2 error is failing to reject H naught when you should have. Right? In terms of our jury trial, right? And actually, we'll see that down here in just a second, and we'll get to that. We don't have to worry about writing it down now. But so type 1 is rejecting H naught when it's true. Type 2 is failing to reject H naught when it's false. A way to remember this is that in a type 2 error, it's when we fail to reject. Type 2 fail to reject H naught. So there might be a way to try to remember which one is which. Excuse me. Okay? Now, if an error is made in a test, does that mean that we screwed up? And the answer to that's no. It's not anybody's fault when we make a mistake. There wasn't, as long as the data is collected properly and certain conditions are met, which we'll talk about later, then it's not really anybody's fault. It's just what the sample produced. And so, but there's still errors, right? I mean, it's still possible that we end up making wrong conclusions. So we have to be aware of that, and we have to try to prevent one of those two errors from happening. We'd like to prevent both of them from happening, but as we're going to see in a minute, that's sort of a push-pull type relationship between those two types of errors, okay? So we failed to reject is one way to look at it. There's also a Punnett square that we can fill in that might help those more of a science mind, might make more sense out of this, right? So along the columns here, we're talking about the truth about the population, and across the rows, we're talking about the decision that was based on the sample produced, right? And so if H naught is true, if the null is true, and then we reject H naught, that's your type 1 error, right? And if H naught is true, and we fail to reject H naught, then that's a correct statement. That's a correct conclusion. That's what we want to. That's what we want to have happen, right? And so, along those same lines, if H naught is false and we reject H naught, then that's good. That's what we want to do, right? But if H naught is false and we fail to reject it, then that's where our type 2 error is. We failed to reject, we're going to make a type 2 error. Okay? Okay, so in this next example, we're back into our jury trial, right? So in a criminal trial, a defendant is presumed innocent until proven guilty. We talked about this. Therefore, our null hypothesis is, and that null hypothesis is that the defendant is innocent, right? That's the claim. It's a statement, our statement of no difference would be that he is innocent. It's what we're supposed to believe, right? What is the alternative hypothesis? It's obviously then that the defendant is guilty, okay? Describe a type 1 and type 2 error and explain the consequences of each. And this is where you're going to make a decision on your significance level, which error you think is most egregious. A type 1 error is that the defendant is innocent but found guilty. Remember that a type 1 error is rejecting H naught even though it was true. So rejecting the null even though the null was true. So a defendant is innocent, but we found him guilty. The consequence of that is an innocent person could go to jail. On top of which, and we discussed this also, if that happens, then the person who actually committed the crime is still running around out there. Right? A type 2 error is that we fail to reject the null, even though it's false. Right? So here is, if we fail to reject the null, then we find them not guilty. And when in fact the defendant is guilty, and so a guilty person is set free. Okay. Now, what I was the connection I was trying to make before is the defendant is guilty but found not guilty, and the reason why we say it like that, and the reason why very often in jury trials when the verdict is handed down, they will either say guilty or not guilty or innocent. Because again, we're never going to accept the null hypothesis. We're either going to reject it or we're going to fail to reject it. Because the sample will either give us enough evidence to reject it or it will not give us enough evidence and we'll have to fail to reject it. It's not, the sample will not tell us for sure if the claim or if the null hypothesis is actually true. Okay? So I think that's a distinction that is important to make there. All right. Now, which of those two is worse? We discussed that a type 1 error here is probably more egregious. And so what we do is we try to, in our legal system, block for that type of error. An innocent person could go to jail. We don't want to do that. So we do make it a little bit harder to, for a jury to reach a guilty verdict, right? That way we don't start sending a bunch of people to prison and find out that there's more that were actually innocent than there really should have been. Okay. So we block for that, and that's what we do when we set our significance level. We're going to block for that type of error if we think that's more egregious. Okay. So. Another type of situation here, if you wanted to go skydiving, you would assume that you have a working parachute. Okay? Therefore, our null hypothesis is the parachute works. We're going to assume that's our null statement of no difference. Someone hands you a parachute, you're going to assume that it works. What is the alternative hypothesis? Well, the alternative is that the parachute doesn't work. Okay? Now, describe a type 1 and type 2 error and explain the consequences of each. Okay? You can stop the video at this point and give it a shot yourself, which would be a good idea, and then restart it again and see how you did. I want to keep going. A type 1 error means that you reject the null even though it's true. So if you reject the idea that the parachute works, then you're going to decide that you're not going to take a working parachute, you're not going to go jump, right? Because if you believe the parachute is faulty, then you're not going to go skydiving still, right? The consequences of that is that you lose money and your friends make fun of you because, especially if this is a group of guys, there's always a bet involved. And if you don't go through with it, your friends better make fun of you or they're not a good group of guy friends. That's part of the fun, making fun of someone who won't go through with the bet. Okay? But anyway, that's it. You're going to lose maybe some money and your friends are going to make fun of you, which, you know, you'll get over, I guess. But if you make a type 2 error, we're going to fail to reject the null. We're going to go ahead and take a parachute and jump even though the parachute doesn't work, even though the parachute's a bad chute. And what's the consequence of that? Well, you jump and die. So which of those two is worse in your mind? Well, for me, type 2 error is probably more egregious here. I can handle a little bit of ridicule. I don't think I can handle death. So I'm going to block for making that mistake, right? I'm going to make it easier to reject the null, right? And that's the idea behind setting your significance level, right? What is the probability of a type 1 error? Okay? Well, if we state a type 1 error in terms of a conditional probability, right? State as a conditional probability, so the probability that we reject H naught, given that H naught is true, okay? You can kind of think about this in terms of when we reject H naught, right? When do we reject H naught? Well, we reject H naught when we reject the null when the p-value is less than the alpha. So that alpha level becomes our cutoff between rejecting H naught and failing to reject H naught. So how is the only way we can possibly make a type 1 error? That's if we reject H naught. So that alpha becomes our cutoff between making a type 1 error or not making a type 1 error, right? So it hopefully makes a lot of sense that the probability of making a type 1 error is just equal to alpha, right? It's going to be equal to our significance level. Remember, this is our significance level. Okay? So how do I want to limit making a type 1 error? I'm going to set a larger alpha, right? A larger alpha means, oh, sorry, not a larger alpha, but a smaller alpha. A smaller alpha means that it's harder for me to reject H naught. Okay? So, you know, if the type 1 error is decided to be more egregious, then we're going to make sure that our alpha level is decreased to where it's a little bit more difficult to get under that alpha level and reject H naught. Okay? Now, what can we do to reduce the probability? Well, I just said it, right? What can we do to reduce the probability of a type 1 error? To reduce type 1 error, demand that the evidence be very convincing before we reject H naught. Okay? Our alpha levels could be anything from, 10%, some popular alphas, 10%, 5%, or even 1%, right? So my p-value would have to fall under 10% or 5% or 1%. Well, obviously it's a lot harder to fall under here, right? It's a lot harder to get a p-value that is less than 1%. So I'm going to drop my significance level in order to make it more difficult to commit a type 1 error. If I don't think type 1 errors are that big a deal, then I can raise my significance level up. And we'll talk about what consequence that has. Okay? All right. Are there any drawbacks to this? Making it harder to reject H0 means that we are more likely to make a type 2 error, right? If we make it harder to reject H0, then on the flip side, it should make sense that it's going to be easier to fail to reject H0, right? If the p-value has to be under that alpha to reject H0, then obviously any p-value above that alpha is going to fail to reject. So if we make it harder to reject H0, that means that we're making it more likely to make a type 2 error. There's that push and pull that I was talking about before. So there are some consequences to doing that. Okay? Now, let's see. What is the power of a test? Okay? The power of a test is, again, another conditional probability, but it's the probability that we reject H0 given that the parameter equals some alternative value. In other words, it's the probability of correctly rejecting H0. We can say that a different way, right? The power is the probability of correctly rejecting the null hypothesis, right? So the power, again written as a conditional probability, the probability that we reject H0 given that H0 is false. This is what this means. The parameter equals some alternative value. This basically means that H0 is false, okay? Now, if you wanted to calculate the power of a test, right? Well, it all depends on the probability of making a type 2 error. We go back up to type 2 error. Type 2 error is that you fail to reject H0 given that H0 is false. So it should be the exact opposite. If you look at this in terms of a conditional probability, a type 2 error is the probability that we reject, the probability that we fail to reject H0 given H0, given that H0 is false, right? That's a type 2 error. It's the probability that we fail to reject H0 even though we should have because H0 is false. Well, these are just complementary events. So if I know the probability of getting a type 2 error, then the power of the test is just 1 minus that. That's the probability that we're going to correctly reject H0. Okay? All right. And then how is power related to the probability of a type 2 error? Well, that should make a lot of sense, right? The probability of a type 2 error increases, then power is going to decrease, and vice versa. As power increases, a type 2 error decreases. Okay? And so think about, as power increases, we become more and more likely to reject H0 given that H0 is false, which means that we are less likely to fail to reject H0 even though H0 is false, and that's our type 2 error. So as power increases, type 2 error decreases. Okay? Now, will you be expected to calculate the power of a test on the AP exam? And we'll for right now say no, because you are not very often going to be asked to calculate a type 2 error directly. Okay, what may happen, what could happen, is that you could be asked about the relationship between power and type 2 error, in form of, if we know that there is a 22% chance of committing a type 2 error, what's the power of a test? And that just becomes 1 minus 22%, which is 78%. So, you know, you may be faced with a situation like that, but we're not going to calculate it directly in terms of getting into a normal distribution or anything like that. Okay? So don't have to worry about that too much. Just understand the relationship between the two. And in just a second, we're going to talk about some factors that affect excuse me, the power of a test. You need to understand how some of these factors affect type 1, type 2, and power, and at least in terms of conceptually, if not numerically, okay? And those factors are the 4 factors that affect the power of a test. And you know, think about the power of a test as how strong the test is, right? The strength of the test is only indicated in correctly rejecting H naught, right? So if H naught is false, then the test should pick it up, should pick up the fact that it's false and reject it. That's the power, okay? So if the sample size increases, then we have this sort of, we know that if sample size increases, it drops the variability of the sample distribution, so it makes it more narrow, right? And consequently there will be less overlap. And we're going to take a look at an applet in class that will sort of explain that a little bit more, okay? But as sample size increases, then it will increase the power of a test, okay? The significance level, increasing alpha, making it easier to reject H naught, will increase power, right? Again, we want to reject H naught if H naught is false. So obviously, the more likely it is, or the easier it is to reject H naught, the more powerful the test becomes. Of course, again, it does increase your type 1 error probability, but it does increase the power of the test. Okay? The next factor, the effect size. What that means is if the true value of the parameter is farther away from the hypothesized value, it will be easier to detect the difference and reject the null hypothesis, right? In other words, if someone hands you a parachute and it looks like, you know, everything is neatly fastened together, the pack is, it doesn't look like it's bulging out anywhere, it looks basically like a parachute might look, then obviously it's going to be harder to reject the idea that the parachute is bad, even though it is. On the other hand, if someone hands you a parachute and you know, the clamps are crisscrossed and part of the parachute's hanging out of the bag, and some of the strings that are supposed to hang the parachute or supposed to attach the parachute to the pack are severed and hanging out the side of the bag, then it becomes a whole lot easier to reject the fact that the parachute is bad. So that's what we mean by the effect size. The further away the parameter value is from the assumed value, the easier it becomes to reject the null hypothesis, and therefore the more powerful the test becomes. Okay? Now, other sources of variability. If we can collect data in a better way, right? If we can have a little bit more of an idea of what's going on, maybe a stratified sample, or if we block in experiments, then it will be easier to see the difference between the true and hypothesized values, okay? Now, a lot of our procedures are based on SRSs, and a lot of our calculations are based on SRSs, but If there is a better way to sample or a better way to assign to treatments, then obviously we're going to take that, and there are ways to account for that type of sampling and that type of assignment. It's just not ways that we're going to concern ourselves with in a basic level AP stats class. So, but there are ways of better sampling and better assignment that could increase the power of your test, okay? And so that's it for the first section. That's it for the basics of hypothesis testing. We'll start in the next section actually putting together tests, and we'll test for population proportions in the next section, and then population means in the third section, and start physically doing and performing the tests. Okay? Have a good night. Homework is in the text, and we'll see you guys in the next class period.